Hello everyone, my name is Edmond.irani. I'm from Technical University of Munich and a member of Cyber Physical Systems Group. This work is funded by the German Research Foundation and the EU Horizon 2020 project. In this paper, we propose a provably safe cooperative driving method for a group of vehicles using invariably safe sets. Cooperative motion planning of autonomous vehicles offers great benefits, which include enhanced road safety, passenger comfort, traffic throughput, and many more. As cooperative motion planners generate trajectories for multiple vehicles, they can more easily find feasible and better solutions for the group, while also taking the individual goals into consideration. All planned motions need to be collision-free with respect to the unknown future motion of other non-cooperative traffic participants. As a consequence, provably safe guarantee for cooperative vehicles in mixed traffic scenarios is one of the major challenges. In our previous work, we have shown that in the case of single vehicle, driving in its invariably safe sets, or ISS for short, ensures that it can remain safe for an infinite time horizon. A natural idea that follows is to extend the notion of ISS into the setting of cooperative driving, which is the goal of this paper. We aim to derive a negotiation and distribution mechanism of ISS for a group of cooperating vehicles. Before proceeding to our method, we first introduce related definitions as the preliminaries. In this work, the ISS of vehicles are computed over their individual reachable set, which is the set of all states that can be reached starting from an initial set of states. A state of a vehicle includes longitudinal and lateral positions, velocities, and accelerations in the road network. The collision-free reachable set that does not collide with the occupancies of other traffic participants is expressed by the following formula. A snapshot of an exemplar reachable set is shown in the figure. The reachable sets of vehicles are projected onto the position domain to retrieve the longitudinal and lateral positions, which are called the drivable area. In the illustration, you may observe the drivable area of the ego vehicle over time, which are depicted by axis-aligned rectangles. Next, we introduce the notion of invariably safe sets. Consider the case that a vehicle is driving with a high velocity towards a static obstacle in a near distance. Although the vehicle is in its collision-free state at the current time, it will eventually collide with the obstacle. To formally ensure its safety, we therefore require the vehicle to be at an invariably safe state. The ISS of a vehicle is the set of invariably safe states that allow the vehicle to remain safe for an infinite time horizon. In most cases, determining the maximal ISS is a computationally intensive task. Nonetheless, its tight-under approximation can be efficiently derived using sets of safe states that respect the safe braking distances and safe evasive distances respectively. These sets ensure the safety of the ego vehicle even if its preceding obstacles and following obstacles brake or accelerate with their maximal capability. Our method for provably safe cooperative driving consists of three major steps. Step 1. Computation of ISS for each of the cooperating vehicles. In Step 2, we derive the safe maneuver corridors for vehicles based on their individual ISS. The potential conflicts of corridors are also examined in this step. Lastly, in Step 3, we negotiate and distribute the conflicting corridors so that in the end every vehicle obtains a negotiated ISS in which to plan their motion. In the upper figure, both vehicles have non-conflicting ISS in their respective lanes. However, the safe maneuver corridors derived from the ISS are conflicting. After negotiation, depending on the distribution result, the two vehicles may plan different sets of safe trajectories. The ISS of each cooperative vehicle is computed with regard to the future occupancies of other non-cooperating vehicles. These occupancies are obtained with the help of a set-based occupancy prediction tool named SPOT, which captures all feasible behaviors of other vehicles. Here we show the construction of the safe braking set and the safe evasive set for a vehicle driving in a lane. In the first rows, we can see that the longitudinal and lateral positions as well as the velocities are all bounded. These constraints are extracted from the reachable set of the vehicle. In the second and the third rows, the vehicle has to respect safe braking distances and safe evasive distances with regard to its preceding and following vehicles. This is better illustrated with a figure. A vehicle has a drivable area covering lanes 1 and 2. In lane 1, it has a preceding vehicle and a following vehicle. The boundaries of the safe braking set and safe evasive set are depicted with solid and dashed lines respectively. The potential future collisions between the cooperative vehicles can be detected by examining the space and time required by the vehicles to perform safe braking or safe evasive maneuvers starting from their respective ISS. This is referred to as their safe maneuver corridors. This is similar to the notion of a driving corridor, except that the initial state of such a corridor should be within the ISS. For the sake of computation efficiency in detecting the conflicts, we obtained a bounding box of the computed safe maneuver corridors. In the figure on the right, the two vehicles have conflicts of maneuver corridors in the middle lane, which forbids them to perform an evasive maneuver. Next, we explain the negotiation of conflicting corridors. Firstly, we generate all possible plans to allocate these corridors to vehicles. In this figure, two conflicts between three vehicles are detected. Note that the first conflict happens between vehicles 1 and 2, and a second conflict between vehicles 1 and 3. By taking the Cartesian product of the coalitions, a total of 4 possible allocation plans can be generated. Each element in the plan denotes the winner of the corresponding conflicting corridor. Given an allocation plan, those states within the ISS of the losing vehicle whose safe maneuver corridor intersects with the allocated corridor shall be removed, thus resulting in a reduced negotiated ISS. After this, we compute the cost associated with each plan. The adopted cost function includes 2 terms. The first term represents the variance of the volumes of the negotiated ISS of vehicles with respect to Plan P, which reflects the fairness of the allocation plan. In the best case, this term equals to 0, implying that all of the cooperative vehicles received equally large ISS. The second term sums up the maximum length of the corridors of each vehicle, which promotes the overall advances in the driving direction. These 2 terms are associated with an user-defined weighting factor. After evaluating the cost of every possible plan, the one with the minimal cost is chosen as the optimal allocation plan. Next, we demonstrate our method on several traffic scenarios taken from the CommonRoad benchmark suite. The first scenario illustrates a highway with 2 communicating vehicles V1 and V2 in the presence of 2 leading non-cooperative vehicles. In the subplots for time step 1 and the planned trajectories, we show the initial positions of the vehicles. In other cases, the drivable area. V1 and V2 face a conflict of maneuver corridors at the very first time step. Our algorithm allocates the conflicting corridor to V1. As the drivable area of V1 progresses to lane 2 at time step 10, another conflicting corridor arises, which is then allocated to V2. The negotiated ISS demand that V2 keeps driving straight, while allowing V1 to choose freely from keeping its lane or swerving into the middle lane. The figure on the right visualizes the negotiated ISS and the states of the planned trajectories of vehicle 2. As can be seen, its states are all within the negotiated ISS, thus safety is ensured. Alternatively, one can only use the negotiated ISS in the last time step if the safety within the planning cycle is already ensured by the motion planners. In the second scenario, V1 and V2 approach a merging point at the roundabout. Note that for complex road geometries, the maneuver corridors of vehicles are projected onto the intersecting lanes to compute the conflicts. V1 gets the conflicting corridor allocated at time step 6, and hence is entitled to keep driving along its lane in the subsequent time steps. On the other hand, the ISS of V2 is constrained to remain right in front of the merging point before V1 passes through. Our last scenario demonstrates a safety-critical situation. A truck driving in the rightmost lane had an accident, causing it to block the two rightmost lanes. V1 is already too close to the truck to perform a safe braking maneuver. The only way that V1 can remain safe is to perform an evasive maneuver with the help of V2. Even in such a critical situation, our method can determine the correct coordination between V1 and V2 to ensure safety. Similar situations can arise due to the presence of unexpected pedestrians, construction sites on roads, and so on. To conclude, we have proposed a negotiation and distribution mechanism of ISS for a group of cooperating vehicles, which can be integrated with arbitrary planning algorithms to generate vehicle trajectories, ensures the safety of the group for an infinite time horizon, and is computationally efficient and works in mixed traffic situations. With different scenarios, we demonstrate that our method ensures the overall safety of the cooperative group, while not overly restricting the set of possible trajectories for the vehicles. Possible future work and extensions include devising a more sophisticated cost function to account for more realistic factors on roads, validating the proposed method on large amount of test scenarios for statistical analysis, and also consider other aspects of safety, for example, formalized traffic rules. Thank you for watching.